Welcome back, everyone. This is Dr. Milian MAMTamayao-Kieke, your instructor. We are now on to the second part of Unit 1, Foundational Concepts. In this video, we're going to continue the discussion of principles of experimental design. Next, we will go through some guidelines for designing experiments. And then we will end the video with a summary of key items to remember when designing experiments. But before we start with this lecture's topics, let's first have a review question. What are the three principles of experimental design? Do you remember? Recall that the three principles of experimental design are randomization, replication, and blocking. Last lecture, we discussed randomization, which basically means that in designing experiments, the experimenter should see to it that the allocation of material and the order in which observations are obtained do not follow a pattern. Let's move on to the second principle. The principle of replication means that repeat runs of each factor should be independent. There are two important properties of replication. First, it allows estimation of the experimental error, and this estimate of error is used as a basis for determining whether observed data are truly statistically different. Second, it allows precise estimation of the true mean. Now recall the metallurgical experiment from last lecture. Can you describe a replicate in this experiment? How many observations are needed if we have 5 replicates? In what sequence should these observations be performed? Okay, let's answer these questions. A replicate would be treating a specimen by oil quenching and treating a specimen by saltwater quenching. And how many observations are needed if we have 5 replicates? We would need 10. 5 for oil quenching and 5 for saltwater quenching testing. Last, in what sequence should these observations be performed? They should be performed in no particular sequence. Also, make sure that consecutive runs do not have exactly the same levels for some factors. Remember that the variability associated with heating and holding factor levels can contribute to experimental error. You might get confused with the term replication and repeated measurement. It is important that you know the distinction between the two. As Montgomery describes, replication reflects sources of variability both between runs and potentially within runs. Let's look at this example. Suppose that a silicon wafer is etched in a single wafer plasma etching process, and a critical dimension or CD on this wafer is measured 3 times. These measurements are not replicates. They are a form of repeated measurements, and in this case, the observed variability in the 3 repeated measurements is a direct reflection of the inherent variability in the measurement system or gauge, and possibly the variability in the CD at different locations on the wafer where the measurement were taken. Let's look at another illustration. Suppose that as part of an experiment in semiconductor manufacturing, 4 wafers are processed simultaneously in an oxidation furnace at a particular gas flow rate and time. And then, a measurement is taken on the oxide thickness of each wafer. Once again, the measurements on the 4 wafers are not replicates but repeated measurements. In this case, they reflect differences among the wafers and other sources of variability within that particular furnace run. Remember, replication reflects sources of variability both between runs and potentially within runs. So, what would you have done? What would you have done to obtain actual replicates in the 2 examples above? Now let's move to the third principle of experimental design, which is blocking. Blocking, as Montgomery describes, is a design technique used to improve the precision with which comparisons among the factors of interest are made. It is used to minimize or eliminate the variability brought about by nuisance factors. And what are nuisance factors? These are factors that we are not directly interested in, but may influence the experimental response. And typically, each level of nuisance factor becomes a block. For example, let's look back to the metallurgical experiment, where the experimenter wants to determine whether the quenching medium influences aluminum alloy hardness. Suppose that the alloy coupons or the test specimens arrive in two batches, batch 1 and batch 2. There could be some variation in the way the specimens in these two batches were produced. Because of this variation, the behavior of the specimens to the quenching media might be affected, and we are not interested in this variability. Thus, the batch is a nuisance factor. To eliminate or minimize this effect, we should perform blocking. In this case, the blocks could correspond to the two batches. We have now covered the three principles of experimental design: randomization, replication, and blocking. Now let's go through some guidelines for the different steps for designing experiments. These guidelines are summarized in this table from Design and Analysis of Experiment by Montgomery. We have 7. First, we have recognition of and statement of the problem. Second, selection of the response variable. And third, choice of factors, levels, and ranges. These first 3 are steps conducted before the actual experiment is performed. These are steps during the pre-experimental planning phase. This phase is very important and must be given a lot of thought and effort. Experimental success relies heavily on how well pre-experimental planning is done. Okay. The fourth step is choice of experimental design. Fifth, performing the experiment. Sixth, statistical analysis of the data. And seventh, conclusions and recommendations. We will now discuss each of these guidelines. The first step in the pre-experimentation planning phase is the identification and statement of the problem. The experimenter has to identify what kind of problem is being tackled. We have 5 broad categories of these problems. 1, we have factor screening or characterization. 2nd, optimization. 3rd, confirmation. 4th, discovery. And 5th, robustness. A factor screening or characterization problem is one where experimenter tries to identify which factors have the most influence in the response or responses. Meanwhile, optimization is where the experimenter identifies the levels of the factors at which the most desired values of the response can be obtained. And then third, confirmation problem is one where the experimenter wishes to verify the assumed or expected effects of factors to the response based on theories or previous experiments. This can be relevant when a project is taken from a laboratory scale to a commercial scale. The experimenter would probably want to know whether the patterns or relationships that were observed in the laboratory are carried over in the commercial setting. And then we have discovery experiments, where the experimenter might be interested in the behavior of new materials or the effects of new factors or range of factors. And then lastly, we have the robustness problem, where the experimenter would want to know what levels of the factors lead to unacceptable variability in the response variable. We could also think of this kind of experiment as one where we try to determine what factor levels enable us to minimize the variability in the response. Next, we use process knowledge and past experience to determine what variables can provide useful information regarding the process under study in the context of the identified problem. We ask questions such as what parameter of the output should be included in the study, or what response variable should be included. Of course, it is not unusual to have several response variables. Next, we could ask how will the response be measured, and how will the measurement system be calibrated, and how can this be maintained throughout the experiment. We want to make sure that we minimize that variability that comes from our system of measurement. The third step in the pre-experimentation planning phase is choosing the factors, levels, and range. Factors that can influence the performance of the process or system can be either potential design factors or nuisance factors. The potential design factors are those that the experimenter may want to vary in the experiment, and these factors can be further classified into design, held constant, and allowed to vary factors. Design factors are those that are selected for the experiment. Meanwhile, held constant factors are those that may have an effect on the response but is not of interest in the study. Thus, they are held constant. Now, allowed to vary factors are those that may impart relatively small variability into the process and may be balanced out or canceled out through randomization. An example of this is the unit-to-unit variability among specimens in the quenching experiment. And then nuisance factors are those that may have significant effects on the response but are not of interest in the study. They can be controllable, uncontrollable, or noise. The blocking principle can deal with controllable factors. In choosing factors, levels, and ranges, we can use tools such as fishbone diagram. And we have to remember that it is best to keep the number of factor levels low. Experimenters can use a cause and effect diagram or fishbone diagram, such as what you can see on the screen, to help in pre-experimental planning. This fishbone diagram from Design and Analysis of Experiment by Montgomery was used to help in planning an experiment to resolve problems with wafer charging encountered in an etching tool used in semiconductor manufacturing. As depicted by the spine, the effect of interest is wafer charging. Meanwhile, the potential design factors are organized into measurement, materials, people, environment, methods, and machines. Some of these factors might be chosen as design factors, such as wheel speed, gas flow, and vacuum, and others might be held constant or blocked, such as temperature and humidity. This is another example of using fishbone diagram for exploring potential design factors. This one was constructed to help with an experiment to study the effect of several factors on the turbine blades produced on a computer numerical controlled or CNC machine. As you can see, the spine shows the three response variables, namely blade profile or profile here, surface finish, and defects. The causes are grouped into controllable factors from which the design factors for the experiment may be selected, uncontrollable factors whose effects will probably be balanced out by randomization, nuisance factors that may be blocked, and factors that may be held constant when the experiment is conducted. Another pointer to remember when choosing factors, levels, and range is that it is usually beneficial to involve an interdisciplinary team. This is to enable collection of a wider perspective. For instance, often neglected, operations personnel and process owners usually have great insights due to their intimate understanding of the process. The next step is on the choice of experimental design. This involves the determination of the number of replicates and the sample size. It is also the step where the run order for experimental trials are set. Now, most statistical softwares actually have a feature to help in generating a run order. Another concern in this step is to determine whether or not to block or whether there are randomization restrictions involved. And lastly, the experimenter also has to identify a tentative empirical model to describe the results of the experiment. Okay, so we're now on to the next step, performing the experiment. A few pointers on performing the experiment include checking and ensuring the correctness of factor settings before each run. It is suggested that there is someone assigned to this task. It is also suggested to perform pilot runs or a smaller scale of the experiment in order to gain information on things like consistency of experimental material, a check on the measurement system, a rough idea of experimental error, and an opportunity to practice the overall experimental technique. Another importance of the pilot run is that it gives the experimenter the chance to revisit the decisions made in steps 1 to 4 and, if necessary, iterate on it. It is important that the experiment is monitored and to make sure that it is conducted according to plan. Errors in following the plan can actually result in loss of validity of the entire experiment. Next is statistical analysis of the data. This is done in order to achieve objective conclusions given experimental results. It is usually wise to start with graphical methods in this step. This is also where the hypothesis testing framework, hypothesis testing, and confidence interval estimation are employed. These are done to help achieve a conclusion that is backed by statistically significant evidence. It is also helpful when an empirical model can be presented based on the data to express the relationship between the important design factors and the response. Other important statistical techniques are residual analysis and, of course, model adequacy checking. These will be discussed in subsequent units. Okay, take a pause and answer the following. True or false? Statistical methods can prove particular effects of a factor or factors. Enter your answers in oblate. The last step in the guideline is the formulation of conclusions and recommendations. The first guideline under this step is that the experimenter must draw practical conclusions based on the results of the analysis and recommend a course of action. It can be helpful to use graphical methods in presenting the results to others. Moreover, in order to validate conclusions from the experiment, the experimenter should perform follow-up runs and confirmation testing. It is suggested that experimenters stick with simple experiments, and as a general rule, no more than 25% of resources should be devoted to the first experiment. As such, iteration is advised and sequential experiments may be necessary. So those were the 7 steps for designing an experiment, along with some guidelines. Now let us close this lecture with some important pointers to remember. First, always remember to use your non-statistical knowledge in defining the problem as well as performing the other steps of designing the experiment, such as identification of factors and factor levels. And it is also emphasized that experimental design and analysis should be kept as simple as possible. Coming up with complex designs and performing ultra-sophisticated analysis to showcase your knowledge may get in the way of actually solving the problem. Next, it is also important to recognize the difference between practical and statistical significance. Results may be statistically significant, but the experimenter should go beyond this and investigate how recommendations based on these results will impact the organization in a practical sense. And lastly, experiments are usually iterative, so prepare to gain insight along the way and be ready to perform further experiments when the situation calls for it. That's it for this lecture. The next video will be the last lecture under Unit 1. In that video, we will discuss sample and sampling techniques.